Good afternoon, everyone. For those of you who are working on the homework assignments, you might have noticed that last night the homework for chapter 4 ended. Anybody got stuck not completing that? Quite a few of you. Okay, if I give one more day, will you be able to finish it? Yeah, okay. Or maybe I'll extend it until tomorrow. That'll probably be better. After class, I'll extend that so people can finish the homework, because I think people are struggling to the end. How many of you waited till the last minute to do it? Okay, some honest people in the back. I'll extend that for you because I want to make sure you are able to go through that, because I think the homework is not just about me collecting points. It's about you being able to work problems and learn materials. So I want to make sure you all have access to do that. So look for that later. Question? So in the overall grade, I'll take all the homework together and make that's 10% of your grade. Yes?
Does the grading just add a couple of points to rest times?
Well, it'll be a total of 10% of the whole grade, so whatever that is. Yes, I mean, it would add up to the total grade for the score for the course. So I'm not sure how to quite answer that, but I would think so.
Just our homework.
Right, it's hard to say because I'll add that all in at the end and just make it 10% of the total. So I would think so, but I haven't done the calculations to see if that really holds true. Any other questions about homework? How many people still struggle with understanding resonance? Quite a lot of you also. There were homework problems on it, and I did have a fair number of questions about resonance on the homework problems. So maybe I'll just take a couple of minutes and go through a little bit of information about resonance and what to look for. When you're trying to see where electrons and charges are in a molecule and how they're spread out, it is important because we're going to be getting into the next chapter today, which is on aromatic compounds, and having a good fundamental understanding of resonance is going to be critical for that. So I think some of the questions I've had regarding resonance in the homework is really trying to identify where electrons are spread out. So just remember, when we're looking at representing molecules with resonance structures, we're looking at the distribution of electrons throughout a pi system. Okay, so pi electrons. And I'm not being able to write very well. Pi electrons. So what that means is anytime you have conjugation, carbons that are adjacent to each other with p orbitals on every carbon, in the case of some of the homework problems, this was like a double bond next to a plus charge or a free radical. I think some of your problems were with free radicals or carbocations. It's focusing in on the part of the molecule only where those pi bonds are. So if people were trying to draw structures where they're putting radicals on carbons that were sp3 hybridized, that's not going to work. You don't delocalize out to there. It's only within the pi systems, which are conjugated, that you're looking at trying to determine what resonance contributors make up the structure. So in this case, let me just draw this a couple of ways. If I were to draw, I'm leaving out the hydrogens for clarity. I'm just drawing the carbons. So you're drawing it like this. It could be a radical plus charge or a minus charge, a pair of electrons. Those are all spread out throughout a 3-carbon unit, basically. If we just focus in on these 3 carbon units, you can draw resonance forms where, in this case, an electron here and here form a new double bond. So notice the double bond is flipping there. Okay? That leaves the carbon that was on the other end of the double bond then deficient. In this case, an electron goes there because we're looking at free radicals. So the other structure of the resonance contributors would look like that. So again, notice what happened in this 3-carbon resonance structure. The double bond moved over, and whatever it is there, a charge, radical, whatever, will move over to the other end of a 3-carbon unit. Okay, people understand this and see this? Okay, well, if that's the case, then what happens if we have more extended systems? One of the problems I think had something like embedded within a molecule. I'm just going to draw something. where you might have generated a plus charge or a radical. Something like this. It's unsymmetric, but we have a plus charge which is next to pi bonds. So if you think about this system, let's see if I can erase some of this. Think about this system here, right? What do we have in terms of resonance form contributors for this? Now we have an extended pi system. So if you think about all of the carbons which are connected by contiguous p orbitals, that'll be pi bonds and things with charges that are next to them, right? So in this case, what we have is all of those carbons right there are connected with p orbitals. So in this case, it's 1, 2, 3, 4, 5 carbons, part of the conjugated system. So in this case, we've drawn one specific position for the plus charge and the double bonds, but there are other resonance contributors because that plus charge is spread out. So in one case, you could flip the double bond over here, and then the charge would end up over on the other end, right? So that would be a one resonance structure, which would look like this. I'll draw it again. Notice I didn't change the other double bond. I've only moved within that 3-carbon unit in each of these steps. So this double bond over here on the right, that was there before, nothing happened to it when I draw that particular resonance form. So again, focusing on that 3-carbon unit as drawing resonance forms for the double bond and a charge. Okay? But that's not the only resonance contributor. We could actually push that charge out to the other side, right? So we push that charge over to the other side, and we have, again, another, let me just undo those. We have another 3-carbon unit over here with a plus charge next to a double bond. You can draw a resonance structure moving that plus charge the other way. Okay, so in this case, I'm running out of room here. The double bond on the left, nothing happens to it when I'm drawing this one, but in the other side, now we've moved the plus charge over to the other end. Okay. Those are 3 contributing resonance structures that represent what is something in between. One thing to look at when you're looking at delocalizing charges or free radicals like this, where are the carbons where the plus charge lies in this extended conjugated system? Notice that for this system, the plus charge, actually we can only draw resonance forms with the plus charge existing on 3 of those 5 carbons. They're every other carbon. So when you draw a resonance form and think about the double bond moving over, the plus charge has to move over, skipping 1 carbon, right? So if you look at any initial structure, you should be able to, hopefully at some point, see this structure here that I've drawn on the right and know that not only do we have plus charge on that carbon, but we have plus charge on that carbon and that carbon as well, as that spreads out. Okay, does that help? Again, this could be in many different orientations. I'm going to clear this and draw another example, which was, I think one of your homework assignments looks something like a ring where, oops, you might have had a double bond there and a plus charge here. Does that look familiar for those who got through this? So where does that plus charge then delocalize to? Well, it can't delocalize over here because this is an sp3 carbon. That's not part of the conjugated system. In this case, we have a 3-carbon system where there are p orbitals contiguously on each carbon because we have a double bond here next to the plus charge. So it's these 3 carbons, which is where that charge is spread out along. And the plus charge is not only going to be on this carbon, but it'll also be skip 1 carbon and then over there. That's where plus charge will be throughout that conjugated system. Okay? So the resonance form for this that would contribute would simply be, let me just clean some of this up here. That double bond shifts over here, and when you do that, what happens to the carbon on the end? It becomes deficient, so that has to be where the plus charge is. So the plus charge is out there. Okay? And again, these are just representations for what is something in between, where, I'm just going to draw it like this, where the 2 electrons and a plus charge are being spread out. Question? Or no? You're just counting?
Oh, well, no, why does the double bond change to, like the first one that you drew, why does the double bond change to a different, like, I don't get why it changes there and the plus moves.
Why it changes in the plus moves? Well, I'm showing the extremes of what exists in between, but keep in mind, on these carbons, let me see if I can draw it on here. In this system, whether I draw it with this structure on the left or this structure on the right, what we actually have is a p orbital on all 3 carbons. Okay, that's the conjugated contiguous one. And within there, there's 2 electrons over 3 carbons and 1 plus charge. And that plus charge, if we're going to draw them with Lewis structures, it either has to have the plus charge on the end carbon in the double bond here, or in the left side, the plus charge on this carbon in the double bond in that position. Those are the 3 carbons that are sp2 hybridized with p orbitals.
Why isn't the top carbon sp2 hybridized?
Which top carbon?
The very top, like in the right.
This has 2 hydrogens on it. It's an sp3. Questions?
Can we do an example where you have like 2 cyclohexenes that were combined in the middle? I think that was on the thing a couple of times. Yeah.
Okay, I don't know exactly the one, but I'll draw something here. So they were fused together?
Yeah. But there was no other branches, just 2 that were fused together like this.
Was it like this?
Yeah, and then there was a double bond on each one of the cycles.
Oh, okay. Like this.
Yeah. So
Okay, so what did the question ask? Draw resonance forms? Or
yeah, I believe that.
okay, in this case, there's no charge or anything else to delocalize, but what we do have is 2 double bonds. Were they doing an addition or something to it?
Yeah, maybe it was
Okay.
the products of the possible products of this or something.
So let's say we're adding HBr to this, right? So when you add HBr to this, notice, I'm going to try to highlight this. Notice we have 4 carbons in a row which have p orbitals on them. Those are the 4 carbons that we're focusing on for reacting with a diene, conjugated diene with HBr. So if you're going to be HBr and you're going to add to this the H+, you're going to generate a carbocation intermediate, right? So you could add it to one of the ends of a double bond. If I were to not have this ring, and I think the problem is when these are embedded in larger structures, it's harder for you to see. If you were to see something like this, and I add HBr to it, you would know you would add H to the end, right? So you'd add, I'm going to highlight the hydrogen. You'd add H to the end, and then you'd have the plus charge there. That's a hydrogen here. On the second carbon, because you broke the double bond. And then you have 2 resonance forms for this. Okay, I'll put that original hydrogen there again. And when you see it with just the 4 carbon unit, you understand that, right? Well, it's the same thing, it's just that this 4 carbon unit is embedded within a larger molecule. So focus in on those blue carbons as the 4 carbon unit of a diene that you're doing reaction in. So if you add HBr to this, the proton goes to one of the end carbons of that diene, right? And I'll just choose to do it onto the bottom one here. So grab the H+, and then you'll add H+ to one end, and you'll have the plus charge, which you'll form next to the other double bond. Okay, here's the other double bond that didn't react. I'm going to draw where the hydrogen added. It already had 1 hydrogen. I'll just draw it both, because now it's sp3 hybridized. And the plus charge is on that carbon. Question?
Is that because the plus charge just always adds to a more stable state?
That's right. Plus charge will always add to the more stable state. So if you add the H plus to this double bond, you'll always do it to put the plus charge to the remaining plus charge to be next to the other double bond. Yeah, that's going to be most stable. So in this case, again, now if we look at this intermediate in the addition of HBr, we have 3 carbons in a row now, that 3 carbon unit I was talking about before, which is conjugated. And so now this plus charge is spread out on the carbon I've drawn it on here and to the other resonance form, which is on the other end of this 3 carbon unit. Okay? So the other resonance form is switch the double bond in the plus charge within the context of the whole molecule. So we can put the double bond here and the plus charge here, and then this is where we originally added the proton. Okay, so these are resonance forms. Okay, does that help? So again, you could have this in large molecules, but look at focus in on where the conjugated system is. So now if we're going to finish this reaction, there are 2 possible products, right? When we add the Br minus, you could add to where the plus charge is shown in the first resonance structure and where the plus charge is shown in the second resonance structure. Those would be 2 possible products.
And the one that would they be equal products, or would one be in higher quantities?
Good question. Would these form an equal mixture? Or would one of the isomers be formed in a higher amount? The higher amount would be formed from the structure of the intermediate, which is a combination of these 2. So do these provide equal contribution to the resonance form?
No.
No, they're different stability, right? Which one is more stable?
Top.
Yeah, top one is more stable because the plus charge is on a more substituted carbon. It's more stable as a tertiary carbocation than as the secondary carbocation on the top. Okay, so in the actual structure that exists in between would have more plus charge on this carbon than the other carbon, although there is plus on both. But you'll get more reaction where there's more plus charge. So yes, you would probably you'd get both, but you'd favor one over the other most likely. That's one of the reasons that would give a different mixture. Okay, any other questions on resonance? Yes?
Did you say that the Br goes where the plus charge is?
Wherever we represent the plus charges in the resonance forms, that's the only places that the Br minus could add to, yes. Okay. Hopefully that helps you to be able to finish the homework. Now I'm trying to figure out how to get back to my presentation. There we go. Well, let's move on and talk about the reactions we discussed before. So remember we were talking about reactions to alkenes and alkynes, and just to remind you what we covered last time, we talked about hydrogenation of alkynes, and under 2 different conditions we have the ability to stop at the alkene stage, which will give us cis-alkene when we have a special poison catalyst that isn't quite as reactive. But if we use hydrogen with a very reactive catalyst that we use to reduce double bonds, it won't stop because the double bond will still be reactive. So 2 different ways to do reduction where we can control where one stops. And then electrophilic additions, very similar to additions to alkenes, except we have 2 double bonds, or 2 pi bonds in which to react with. So it's hard to stop at one, and most often what happens is you get double addition of your electrophile. So in the case where we add HBr to a triple bond, okay, it'll add once, but then that will react again with the same now Markovnikov selectivity we do with respect to addition to a double bond, putting 2 bromines on 1 carbon. Or adding halogens, Cl2, I2, Br2, you'll add 4 of them across where the triple bond was. Yeah,
Is
question?
that showing that that's always going to be trans?
Not necessarily.
All right.
There are other factors involved, that's pretty complicated. But.
All right.
Adding water, like we would do with a double bond, it'll make an alcohol. In this case, what happens is we end up with 2 bonds to oxygen in a slightly different form. And if you can remember it that way, it would be, I might be able to help you recognize that what we get out is a CO double bond, because we're adding, essentially think about it as adding 2 bonds to oxygen instead of 1 bond to oxygen, as if it were an alkene. Okay, so electrophilic addition. And at the end of the last class, we were talking about this reaction. So remember, what's different about alkynes from the alkenes is that the pKa, or the acidity of the hydrogen that's on an alkyne carbon, or an sp carbon, is low enough that if we have a really strong base like sodium amide, we can actually deprotonate it. And this is very useful because what it allows us to do is generate these carbon nucleophiles that allow us to react with other functional groups. This is a reaction we'll spend a lot of time in a couple of chapters. This substitution reaction where a nucleophile reacts with an alkyl halide. But this is very useful for generating carbon-carbon bonds. And we can build up carbon skeletons using this. So notice we've created a new bond in the product. When we react this with methyl bromide or any alkyl halide that's suitable for it, it'll form a new carbon-carbon bond. Okay. What kind of bases are appropriate for deprotonating this? Well, I've drawn one here that's sodium amide. And that's because we need to have a base that's strong enough. If you just think about sodium hydroxide, that's not a strong enough base. Or any deprotonated form of an alcohol, those are not strong enough bases. The pKa, because if you think about the reaction of this plus this, alkyne plus sodium hydroxide, what would the product of that acid-base reaction be? The acetylide plus water, right? Anybody remember what the pKa of alkyne is? pKa of this hydrogen is about 25 or 26. pKa of water?
16.
About 16, yeah. So obviously this is the stronger acid. What that means then is this equilibrium would lie to the left. This is not a strong enough base to deprotonate the alkyne. On the other hand, the reaction on the top, what I haven't shown, is that the conjugate acid is ammonia, has a pKa of about 44. Much larger. So yeah, that would deprotonate alkyne and go all the way to the right. Well, where is this important? Well, we can think about all kinds of different reactions and combining reactions to build up molecules that we desire to synthesize. And there's a whole field of strategizing on how to make molecules most efficiently, which we call organic synthesis. And some organic synthesis is very complicated, often requiring more than one step. But once we have this toolbox of reactions we can do, reactions that will convert one functional group into another, and particularly this reaction which allows us to create carbon-carbon bonds, then we can think about combining them in a sequence to do things that we want to build molecules. So in this case, if you take a look at the molecules I've shown up here, the ones on the left are our starting materials. Let's say, for example, we have acetylene. That's the simplest alkyne, is acetylene, common name. And I want to build the structure that's over here on the right from acetylene. How would you go about doing that? And what do you have to think about to be able to construct that molecule using the chemistry that we've learned so far? Okay, you notice we have hydrogens on both ends of the acetylene molecule. And the product that we want to achieve has substitution on either end. So notice on the left side we have a 2-carbon unit, and on the right side we have a 3-carbon unit. Okay? So in this case it's just a matter of sequentially adding the groups onto either end using the chemistry that we just talked about. we can take these protons off of the acetylene with the right base, and then react it with the right electrophile, an alkyl halide, to put on those groups. Okay, so how would you think about doing that? Well, one of the strategies in thinking about a multi-step sequence, as opposed to just a one-step reaction, which you should be able to see a little bit easier, is look at this sequentially, starting from the product you want to get to and work your way backwards to the starting material. So if we think about the alkyne on the right, let's just work backwards with one of these groups. So let's say in the immediate precursor, I want to take that group off and start with this. Okay. Notice what I did, I'm thinking backwards. So in the last part of the synthesis, I'm going to add the 3-carbon group. So how do I do that? Well, we need to do 2 things here. So in order to carry out that reaction, we need to first take off the proton on the end of the alkyne. And the base we use to do that is sodium amide, NaNH2. And then that intermediate that's generated, that carbon with the minus charge on it, we need to react with the other partner, the alkyl halide, to make the new carbon-carbon bond. So what then would I have to react it with in the second step once I generate that? Any idea? Well, we need this 3-carbon unit, and we need something to make it reactive, a functional group, and in this case we want something like a bromide or iodide. I'll just use a bromide attached to a 3-carbon unit. That's the other thing we have to react it with. Then we will be able to make that new carbon-carbon bond by substituting the alkyne for the bromine. Okay, so if you know those tools, then you can envision that. So now what remains is to think about how we get to this structure in the middle from where we start with. And hopefully that should be easy at this point. We're adding on a 2-carbon unit from where a hydrogen was before. So again, we start with taking off the proton to make the carbanion, and then reacting it with a 2-carbon alkyl halide, like bromoethane. That'll put on the 2-carbon group on the end. So there we just did a synthesis, a multi-step synthesis, using the reactions we've learned in class to build that. Okay. So hopefully you can see that what we need to do is inspect our starting material, inspect our product, try to think stepwise on how we can build up from what we start with. And it's most often useful to start at the product and work backwards, step by step, until you can get to where the starting material is. So now take a look at this bottom one. The bottom one's a little more challenging. What kind of changes or transformations do we need to do from the left to get to the right? So the first thing you look at, well, we have alkyne here on the left. Do we have more carbons? Sure. We've added some carbons on. So we have this, the 6-membered ring plus 2 carbons of the alkyne. And on the right, we have added on several more carbons. In this case, we've added on these 4 carbons. Okay? So somewhere along the line, we're going to have to do one of these alkylation reactions like I described above to put on that 4-carbon group. So notice again, where I've made the bond, the thing I'm going to need to do that eventually, to put this group on, is some alkyl halide where I've connected the bond. So we need probably something like that. Okay? Now, obviously, I don't have a triple bond in the product, right? So I had to do some reaction to change the triple bond into a double bond. So you know which reaction that is, right? You add hydrogen. So one step is going to be an alkylation with this alkyl bromide. Another step has to be a hydrogenation step with a catalyst, in this case to stop at the double bond. If you don't remember yet, it's Lindlar's catalyst. Okay. So those are the two things we need to do. Add on more carbons and then reduce triple bond to a double bond. Now, which order do we need to do them? Which reactions, because if we have these two sequences to do, these two transformations to do, we have to do them in the right order, otherwise it might not work.
Hydrogenation first.
So if we do the hydrogenation first, okay. If we do the hydrogenation first, we'll make this double bond. Do you know of any reaction that can add carbons onto a double bond? No. So you can't add carbons onto the double bond. How do you add on this group to the double bonded carbon? We don't have any tools to do that. So obviously this can't be the first reaction we do, right? Because we need the alkyne to be able to remove the hydrogen and create a new carbon-carbon bond. So instead of that reaction first, what we first need to do is put on the 4-carbon group. So again, first step is deprotonate with sodium amide. Second step is to add this alkyl bromide. Okay? Then the intermediate that we generate from that reaction still has the triple bond, but then we've added on that 4-carbon unit. Okay? Now once we have made that new carbon-carbon bond, now we have no problem at all doing the reduction. And then in the second sequence, the second transformation is hydrogenation with Lindlar's catalyst. Okay? Doesn't do anything to anything else in the molecule because that catalyst only reduces triple bonds to double bonds and then stops. So the other double bond, nothing happens to it. The double bonds in the ring, nothing happens to it. So this is what we do as organic chemists, is think about the best strategies and sequences for trying to build molecules using all the tools that we have in terms of reactions. Sometimes we need to see that you have to recognize, like the double bond in the product must have come from the triple bond, so then we think about how to do that with like a reduction. Okay, or other transformations. What if the product had OH groups in it, maybe, or a ketone? Maybe we needed to do hydration of a triple bond or a double bond, and somehow we have to get to that kind of intermediate. So those functional group transformations we have to think about in addition to those reactions which form new carbon-carbon bonds. Okay, so that's where these alkyne reactions are useful for building up carbon skeletons. We're going to come back to more organic synthesis at the end of chapter 5 when we start to learn about reactions of aromatic rings. And as we continue to build throughout the semester our toolbox of reactions, then we have more things available to us to be able to build all kinds of different molecules. Okay, so let's move on. I want to start chapter 5 and talk about aromatic compounds. There's a lot of information in this chapter, a lot of new reactions. But what we find in aromatic chemistry is that because of special stability in aromatic compounds, we have different kinds of reactions that they do than what we do with typical double bonds. So let's talk about some of the first aromatic compounds, namely benzene. We've seen this six-membered ring structure benzene throughout the semester so far. A cyclohexatriene structure, six-membered ring with 3 double bonds. And the story about benzene actually is quite interesting. There's a lot of folklore about the discovery of benzene and coming up with the structure back when chemists really didn't understand chemical bonding. They really had no idea. They knew that carbon made 4 bonds. They knew about unsaturated hydrocarbons, so they have less than the full number of hydrogens as alkanes. So alkenes and alkynes, ring structures. Benzene was first isolated. People think benzene is this bad molecule, carcinogen, that comes from petroleum. And yes, it has some slight carcinogenic properties and comes from petroleum. But it was first isolated from whale blubber oil in 1825. They used to, before lights, right, they used whale oil to light the lamps. So it was a huge industry. And they isolated this molecule out of that. Michael Faraday did, and they tested this using the chemical test they had at the time and discovered that it was a hydrocarbon that was unsaturated. That means there wasn't the right number of hydrogens to carbons to be a saturated alkane. And they came up with a molecular formula through various chemical tests that showed that it was a C6H6 molecule. 6 carbons and 6 hydrogens. Okay, but interestingly, when they started to test this reactivity of benzene, they found that it didn't do the typical reactions that other unsaturated molecules did. That means molecules with double bonds or triple bonds. So they react with Br2, nothing happens. They tried to oxidize it with permanganate, that we know will react with double bonds, nothing happened. So they didn't know what this was. So a lot of things were proposed, some that were on point, some that were off point. One way to have less hydrogens than carbons is to make rings, because you need to remove 2 hydrogens to connect 2 carbons and not have double bonds. So people were thinking about, well, what structure could have rings but have the molecular formula C6H6? And this was one that was proposed. This has a lot of rings. And each carbon only has 1 hydrogen. So it's 6 carbons and 6 hydrogens. And it would seem reasonable. However, this is a very strained molecule and it would not be very stable. And benzene was a pretty stable molecule. Another structure which was proposed by a chemist named Dewar was this one, referred to as Dewar benzene. 6 carbons, 6 hydrogens. But if we have this structure, we have 2 different kinds of carbons and hydrogens. We have sp3 carbons and sp2 carbons. But people at the time realized that in benzene, it was a symmetric molecule and all the carbons were the same. So that was not, didn't fit with the observations of the molecule. And it was a little while later, in 1865, when the proposed structure for benzene that was a lot closer to what we know benzene is today was given by Kekulé. And he imagined this was a ring of 6 carbons with alternating double bonds. Although they didn't have a good idea about resonance then, about delocalization. They thought these were isolated double bonds and there was an equilibrium of the molecule shifting from the double bonds between those 2 carbons and then all of them shifting one position. In fact, if we actually had that, we would have a molecule with different bond lengths. So if you think about a carbon-carbon single bond, a carbon-carbon single bond is about 1.5 angstroms, whereas a carbon-carbon double bond is shorter, about 1.3 angstroms. So if we did have these alternating double bonds that were in one position and just equilibrating around, and actually this existed, it would not be asymmetric. You would have longer and shorter bonds. In fact, we know all the bonds are identical in benzene. And with our modern knowledge of electronic structure, and we know that all of those p orbitals are connected, the electrons are just delocalized throughout all 6 carbons. We know that that's not an equilibrium, they're in fact resid structures, and the structure of benzene is flat, it's planar, all carbons are sp2, and all completely symmetric. Okay? Now benzene is what we refer to as an aromatic compound. And aromatic compounds, again, before we had a much better knowledge of bonding and structure that we have today, aromatic compounds were compounds that were found in nature to have aromas, obviously, aromatic compounds. That's why they were named that way. A lot of molecules that contain benzene rings and other kind of aromatic rings also had various aromas. So some of the structures that people identified early on, here are some examples of aromatic compounds. Notice all these contain some kind of 6-membered ring with the 3 double bonds in it. Various substituted molecules, aromatic compounds. So for example, this one, benzaldehyde, where we have a aldehyde group, functional group. That's a double bonded oxygen in this short notation. Smells like almonds, and actually it's the molecule that's in almonds that gives the characteristic almond smell. So you can isolate benzaldehyde and use it as an almond flavoring, actually. If you put in between the aldehyde group and 2 carbons with a double bond, this is cinnamaldehyde. Cinnamaldehyde smells like cinnamon. It's a pretty aromatic compound. Cinnamaldehyde is often used as the pure chemical to flavor things with cinnamon and give it the smell. You might have smelled mothballs. That's a pretty aromatic compound. That's this aromatic compound, naphthalene. Naphthalene is a fused, 2 6-membered rings which are fused together with a p orbital on every carbon. Okay, many of those. We'll come back to these, but notice along the top there, I've shown several substituted benzene rings. There are a lot of common names associated with aromatic chemistry due to the history of their discovery and use. So, carboxylic acid group, this is benzoic acid from the benzene. Toluene is a benzene with a methyl group on it. Xylene is a benzene with 2 methyl groups on it. And don't be confused by the way I've represented this. All that indicates, when I didn't actually draw it to a carbon, is that a xylene could be with the carbon on there, or the CH3 there, or the CH3 there. There are 3 different positions where it could be. Phenol. Anybody know phenol? Heard of phenol? It's the benzene with an alcohol functional group on it. Sometimes used in throat sprays and lozenges for sore throats. It's an antiseptic. The nitrogen compound is called aniline. There's a lot of different common names. Some of these you'll have to remember, and others, well, there are some common names that even I don't remember. And aromatic rings can be all kinds of different shapes and sizes. They can be fused together. They can be fused like this. You might have heard of PAHs, about their dangers of PAHs in the environment. Polyaromatic hydrocarbons. They're essentially benzene rings which are fused together, and there are many different kinds of PAHs with different numbers of rings that are fused. This one actually happens to be found in tobacco smoke. So what happens, actually, as a side note, these PAHs, why are they so dangerous? Any idea why they're dangerous? They actually, because of their flat nature, and the fact that the benzene rings are fused together, they actually get metabolized in your liver and oxidized at one position to make an epoxide. And that epoxide, then, these molecules, if they're flat, they slip in between the base pairs of your DNA when they're in the cell. And that epoxide is reactive, and so the the DNA bases will react with it and make a covalent bond. And so they permanently alter the structure of your DNA and cause mutations in your cells. So PAHs can be quite dangerous. Some of them are more dangerous than others. By the way, you know what the other source of PAHs that all of you probably get is? Anytime you burn things, you generate PAHs. So not only smoking, you get PAHs in your lungs, but when you grill steak, guess what that nice flavorful char is on the outside? Well, there's some PAHs in there too. Take that home. But I'm not going to stop eating these. I don't know, any vegans in here, sorry. But they're embedded in all kinds of molecules, as you see, biological molecules, hormones, drugs. There's tons and tons and tons of different aromatic compounds. And their flat nature and structure has a lot to do with some of the chemistry that they do. But these compounds are interesting. As I mentioned, benzene puzzled chemists for a long time until we had a better understanding of the structure and the stability and the reactivity. So I mentioned that benzene doesn't react with bromine. So they just took bromine, just like when you would do any double bond, and reacted with reacted it with bromine, and nothing happened. Okay, so what kind of reaction is that? What kind of reaction is the bromine adding to a double bond? An addition reaction, right? 4 classes of reactions. An addition reaction. So benzene doesn't do addition reactions directly to give those products that we would expect from double bonds. Okay. What was discovered, however, is that if you took benzene and bromine and you used a Lewis acid catalyst, in this case iron tribromide, so Lewis acid catalyst, and heated this up, they did get a reaction with bromine, but not the reaction we expected of a pi bond with bromine. We actually got a different kind of reaction. You know what classification of reaction this is on the bottom? Not a rearrangement. Rearrangement is we haven't lost or gained anything, right? We've just changed. It's a substitution, yeah. So in this case, what we've done is, I'm going to show for clarity, the hydrogen, there's hydrogens on each of those carbons, right? So we've substituted a hydrogen for a bromine. Substitution. Okay, in the process, we get the product bromobenzene, and then the byproduct is HBr. The catalyst ends up unchanged at the end of the reaction, right? That's why it's a catalyst. Question?
Where does the iron go? It's not written.
It's just a catalyst, so nothing happens to it. It just remains at the end iron bromide. It's involved in the reaction, in the mechanism. We'll talk about those details. But at the end, you just get the iron back, iron tribromide back. Okay, so what the heck is going on here? This is not following what we've learned about alkene chemistry directly. Or is it? Well, in some ways it is, and in some ways it isn't. The first step is the same. We get addition of an electrophile to a double bond to generate an intermediate carbocation. The second step is different. Instead of adding Br minus, what we do is we lose the hydrogen and regenerate all 3 double bonds in the ring. And because of special stability, it's hard to break the conjugated triene system in benzene, and if we do it, the lowest energy pathway is to reform it somehow, however the molecule can. So let's take a careful look at benzene and why it's something special in terms of stability because of these conjugated double bonds that we can draw as resonance forms. So benzene is an aromatic compound which is symmetric. The ring electrons in the pi system are all delocalized throughout, as shown in this picture on the right. Notice the electrostatic map. The pi system does have a lot of electron density because there are 6 electrons in those 3 double bonds, in the pi bonds, in the p orbitals throughout. So there's quite a bit of electron density there. But what gives rise to its special stability? And indeed, if you I didn't have this on the slide. If you do combustion, we can get relative energies by comparing the combustion and looking at the energy released, the heat of combustion. What we find is that benzene, if you just think about a molecule like hexatriene, which is 6 carbons with 3 conjugated double bonds, and you compare the heats of combustion for hexatriene versus cyclohexatriene or benzene, you find that benzene has a lot more stable than hexatriene. It's much lower in energy. Okay? And it has to do with a combination of the right number of electrons in a pi system and the fact that they're in a ring and circular. Okay, so many types of molecules actually have the components required to provide this extra stabilization, which we call aromatic stabilization. By the way, the explanation for this involves a lot of quantum mechanics and things like that, so don't worry too much about that. I'm not going to go through it here. But these are the things we have to have in order to have an aromatic compound. Okay, and that shows up with this extra stabilization. You need to have a ring, and that ring has to be flat. In other words, there has to be a p orbital on every atom in the ring that is adjacent, and then those have to be on the same plane. That's why we need a planar ring that's fully conjugated. Okay? Once we have that, we have the potential to gain aromatic stability, but not necessarily. It has to have the right number of electrons. And this came about from trial and error, and Huckel came up with a rule. And now we've shown with quantum mechanics and orbital calculations that this is indeed true, that you have to have the right number of electrons according to this formula, 4n plus 2. N is any integer, so just if you have a series, just plug in an integer for n. So if n equals 0, that equals what? 2. If n equals 1, it's 6. N equals 2, 10, and so on. Okay? So if you have a conjugated planar pi delocalized system that has 4 electrons or 8 electrons or something, it doesn't gain this special aromatic stability. It just has to have this right combination of ring structure, fully conjugated, and the right number of electrons. So look at benzene, 3 double bonds. There are 6 electrons that are delocalized throughout the pi system in benzene. Okay, and most often, in most of the cases we'll see here, 6 electrons is what we're looking for, and will be the aromatic compounds. Okay, so those things, when we have those things together, we get extra stabilization, which changes then the reactivity of the molecule. So take a look at these. Benzene we just talked about, right? Benzene is an aromatic compound. It's quite stable. If you take a look at benzene, 6 electrons, 3 pi bonds. So what I'll say is there are 6 pi electrons, okay, for 2 in each of the double bonds. There's a p orbital on every carbon because there's a double bond that's all contiguous. It's flat. It's aromatic. Okay? Very stable. It won't even react with bromine, Br2, unless you have this catalyst to do a different kind of reaction. Cyclobutadiene. It's got p orbitals on every carbon. They're all contiguous, so it is completely conjugated around a ring. It's obviously flat, but only has 4 pi electrons. Okay, it's not aromatic. Wouldn't be considered an aromatic molecule because it doesn't have the special stabilization from the rings, because we don't have the right number of electrons. As a matter of fact, cyclobutadiene is extremely reactive, and you can't get a bottle of cyclobutadiene. It's too reactive. It'll do all kinds of things. It'll dimerize and try to alleviate its strain through a bunch of different reactions which you haven't even learned yet. Whereas benzene, pretty darn stable molecule. Okay? Well, what about something like this? What about that molecule? Is that an aromatic compound? Heard someone say no? Anyone say yes? Is it a ring? Yes, it's a ring. How many pi electrons are there? 6 pi electrons. Well, that looks good, right? It's a ring. Is it fully conjugated? No. This is an sp3 hydrocarbon here. There's no p orbital on that carbon. So in fact, there's not a circular ring of conjugation. Yes, the double bond is conjugated throughout here, or the 3 double bonds are, but there's not a circle. It doesn't complete the circle. That's the thing we have to have aromatic compounds. Okay, I'll just show you some other examples. Your book doesn't have these, but these are some other examples of ring systems where we could have aromatic or not aromatic systems. That could involve structures that have charges which could allow for a p orbital on the carbon, even with an odd number of carbons. So we showed you benzene here, aromatic, 6 pi electrons. Well, if you go to a 5-membered ring and put a p orbital on it, on that odd carbon by having a carbocation, it's fully, there's a p orbital on every carbon, so it's a complete ring, but there's only 4 pi electrons. Okay. On the other hand, if we had a lone pair there, that could then be involved in resonance structures and delocalize. Now we have 6 electrons, even though it's 2 double bonds and then a lone pair. That's okay. It's a ring, it satisfies all the requirements. Ring, we could have a p orbital on every carbon and a fully conjugated system and 6 electrons. That's aromatic. So cyclopentadienyl anion is actually a pretty stable ion. Same thing with the cation from cyclopropene. It's relatively stable compared to this one, for example. And so on. You can have all kinds of different molecules. This has 8 pi electrons. It doesn't fit the criteria. It doesn't gain the extra stabilization. So actually, it twists to avoid a situation that would be even higher in energy. So it's not aromatic. But then we can have lots of different kinds of ring systems that are aromatic. And we'll talk about it more a little bit later, but these are just examples with all carbons in the ring, but you can have other atoms in the ring as well. You can have oxygens in the ring, you can have sulfur in the ring, you can have nitrogen in as part of the ring. Those, what we call heterocycles. There are a lot of aromatic heterocycles as well. And we'll see that in a little bit. Okay, so let's go back to benzene and substituted benzenes. Here are some of the common compounds that we've seen. Some of these already, and we'll see some more examples of naming and how we identify these structures. So benzene, these are substituted benzenes. So as I mentioned, here's toluene with a CH3 group. And when we talk about naming benzene derivatives, keep in mind if we use this common name, that common name as a parent name for a molecule includes the substituent attached. So when we use the name toluene, it's including the CH3 group. So you don't want to add it also methyl in your name if there's other things on there in your name yet. Phenol, aniline. Here, this one is referred to as acetophenone because it's an acetyl group attached, and it's a ketone functional group. Probably the ones that you'll want to be really familiar with, toluene, phenol, benzoic acid. Those ones you should probably commit to memory and know the structure. This has a carboxylic acid group. I mentioned benzaldehyde. Xylene. So I showed xylene without showing where the second methyl group was. Here's a specific one where the two methyl groups are on 1 and 2 carbons. There's a term here which we'll explain in a few minutes. They use ortho to refer to those being next to each other. Okay. Last time, a couple of lectures ago, we talked about polystyrene. Well, this is styrene. Styrene is the benzene ring with a double bond, 2 carbons attached. Styrene. So you should all be able to tell me what the structure of the polymer is made from that, right? Okay, well, let's take another look at some of these names. Notice in these names, let me just back up one. Another way to name these common names, instead of toluene, you could call this one on the top, what do you think we should call it if we use a more systematic naming? What's this substituent? A methyl. So we could call this methyl benzene, because it's a methyl group on a benzene. An alcohol group could be called a hydroxy substituent, so this could be hydroxybenzene. Okay, or aminobenzene for aniline. Xylene, 1,2-dimethylbenzene. Okay, 1,2-dimethylbenzene. Remember what we would call that as a substituent? Remember what we call that as a substituent? This would be vinyl benzene. So we could name that with benzene as the parent. In many organic compounds we can do that. These common names stick for specific monosubstituted benzenes, and those are often used as the parent name to describe further substitution on there. Take a look at some of these. This also explains a little bit about how we name these compounds. So, obvious reasons, bromobenzene, nitrobenzene with a nitro group and NO2 group, ethylbenzene. Again, name the substituent and then put that on the parent. In all these cases, benzene is the parent molecule, which just consists of the 6 carbons of the ring. Okay, that benzene. Okay, if we have a larger molecule where a benzene ring is a substituent on a larger molecule, we have a name which we refer to as a phenyl group. Don't ask me where that came from, but that phenyl group is what we refer to as a benzene ring, as a substituent on a larger molecule. Okay? Something else you should remember. By the way, when we're drawing structures, we get lazy. Instead of drawing out the whole benzene ring, we often use a pH to represent phenyl. That's a benzene ring, pH. Okay? If that group as a substituent on a larger molecule is a benzene ring with an additional carbon, a CH2, this is what we refer to as a benzyl group. Please don't confuse those. Benzyl includes the CH2 and phenyl doesn't. But that's a name that's commonly used to refer to that as a substituent. Okay, so in terms of benzene names, we can use a lot of what we already know about naming molecules. Just know that the parent is benzene or one of those common names. And we give them numbers for the positions about where things are attached relative to each other. Well, along with the same rules, right? You try to get the lowest numbers. You go around the ring to get the lowest numbers for substituents. Okay, so take a look at this this ring. So if I do something like that, how would you name that molecule? Yeah, it's a benzene with 2 groups on it. One is a bromo substituent, one is a propyl substituent. So in this case, they are 3 carbons apart, and I would probably number it this way. Bromine being lower in alphabetical order, I'd probably do 1 bromo, 3 propyl, benzene. That's a benzene, if you can't read it. Okay, I've given the substituent names and the numbers. Not too hard, right? Well, of course, like everything else, there are a lot of common names and common indicators that are associated that we have to remember in addition to the systematic names. So one of the things that is common with benzene rings when there are 2 groups attached, and only benzene rings when they have 2 groups attached, is a indicator that indicates the relative position. So if we have some substituent on 1 carbon, and we have another substituent next to it, okay, 1-2 relationship. The 1-2 relationship has a common way to refer to that as an ortho relationship. So relative to one of the groups, the next position over, it could be this side or this side, those are what we would refer to as the ortho positions. Ortho, actually 1-2, ortho. So you saw before when we had xylene on that list of some of the common names, it was called orthoxylene because the 2 methyl groups were on 1 and 2 positions. So that's a common way to refer to the relationship between 2 positions. Well, if that group is on the 3rd position away, so instead of here, we put that group here, whatever it is. Now it's a 1-3 relationship. 1-3 relationship. There's a common reference that we make to that relationship between groups, and we refer to that as the meta position. So they're meta to each other. Ortho-meta. And the last position here, when it's a 1-4. The term we use to refer to that positioning is called para. Okay? Ortho, meta, and para refers to 1-2, 1-3, and 1-4 relationship on a benzene ring. So, paraxylene. What would be the structure of paraxylene? Xylene is a dimethylbenzene. And so paraxylene would be wherever you put the methyl group to start with. 1 methyl group there, the other methyl group would be 4 carbons away. Paraxylene. Okay. Metanitrobenzoic acid. What would metanitrobenzoic acid look like?
NO2 on either the 1 and the 3 and then whatever the...
So benzoic acid has a carboxylic acid group, which is CO2H. And then relative to that, the meta position would be either here or here. It doesn't really matter which side I choose. Would be a nitro group. Meta-nitro, sometimes just referred to as M, or you can spell it out. Nitro-benzoic acid. So notice the base structure named benzoic acid includes the CO2H group. Okay, that's my parent. But the relationship, because there are 2 substituents, I have to indicate as either, well, it's hard to say you can say 3-nitrobenzoic acid or meta-nitrobenzoic acid. Either one is correct. Okay? Here are a few other examples of some names and molecules. We could name them in various ways. So, orthodichlorobenzene or 1,2-dichlorobenzene, either one is correct. There's para-nitrobenzoic acid. I just showed meta-nitrobenzoic acid, an example of that. Phenyl in the middle of a ring, or in the middle of a chain, a longer chain, so octane. This is a substituent, so phenyl group on the number 4 carbon of octane. Notice this common name here, biphenyl, where 2 benzene rings are linked by a single bond. When we have more groups, we just give more numbers. So toluene is the parent name that's listed here in red. So toluene includes the methyl group. And when you use that parent name, the substituent that's in the parent name is always considered the number 1 carbon, where that's attached. So here we have 3 nitro groups, 2,4,6-trinitrotoluene. Anybody know the common abbreviation for that? Trinitrotoluene would be TNT, and it's an explosive, so be careful with that. Okay, I'm going to stop there today. We'll talk more about this next time, and then we'll talk about this substitution reaction of aromatic compounds in detail in terms of the mechanism.